Welcome to the class. Today we're going to talk about Windows, and more specifically some of the special features and architecture details of Windows that you need to be aware of when you're building applications or auditing applications or doing anything related to security on Windows. Now, the Windows, there are many classes called Windows internals, and there's a number of books that you can buy that talk in great depth about the internal architecture of the operating system. But a lot of that knowledge is good background information, but it doesn't really focus on the things that are relevant to security. In this talk, we're not really going to cover, the great width of breadth of information that you could cover about Windows. We're only going to focus on a couple of carefully selected examples that kind of show you how you can go down the path of investigating a particular feature and deciding whether it introduces security vulnerabilities or not. A lot of the things that deal with security of applications on a certain platform depend on the architecture of that platform and various design decisions that the platform developers have made. So if you're auditing an application that is intended to run on Linux, you might have the exact same code as what runs on Windows, but it might be vulnerable, whereas the Windows version would be safe, or vice versa, because the underlying libraries and the underlying formats and data structures are different. So let's start with just taking a very, very high-level view of the architecture of Windows. And throughout this talk, I'm going to be making references to Linux and contrasting the two operating systems, because these are the two major operating systems that you're going to encounter. OS X is actually closer to the Unix camp than Windows. So a lot of the Linux, whenever I say Linux, that also applies to other Unixes and to a large extent OS X as well. So in a traditional Unix operating system, you have a very clear separation between the kernel and the user applications. This is not the case on Windows. There is no clearly defined and documented interface for applications to talk to the kernel. This is because on Windows, the kernel does not provide a documented interface that application developers are supposed to use. Instead, Windows provides a number of user space libraries which have the DLL extension on Windows. And these libraries provide various functions that interface between your application and the kernel. So if you look at the structure of the different layers, you have your application. Your application typically would call functions provided by a set of DLLs. Those could be the C++ library, other libraries that your application depends on. It would also call, so those libraries would typically call the underlying functions of the Win32 API. This is the main application programming interface that Microsoft documents and exposes. And those are provided by the standard Windows DLLs, which you'll find in C Windows System 32. And those DLLs include kernel 32, user 32, and GDI 32. These are the three main ones, but there's a number of other ones, and over the years, Microsoft has added many, many more. So most of the functions exposed by these libraries are documented. If you go on MSDN, which is the Microsoft documentation site, you'll find documentations on most of the things that you're supposed to use. But these are not really equivalent to the Unix syscalls, because they don't, when you call a function from kernel 32, for example, it doesn't go directly into the kernel. Instead, the library code in kernel 32 performs some additional functions, and then it calls into a DLL called anti-DLL. Anti-DLL is the interface between the user space and the kernel. So NTDLL implements what is known as the native API. This is the lowest level API that Windows provides, and most of the NTDLL functions are very thin wrappers around the actual kernel interface. So let's take a look at an example. It'll make things a little bit more clear. So these are different layers. So what happens when you open a file? So if you're writing a C program, you might call the fopen function. This is a standard function of the C library. It's available on all C implementations. So on Windows, if your program is compiled using the Visual Studio compiler, this function is going to be implemented in a library called msvcrt.dll. And the parameters of the function are pretty simple. You just have a file name and a mode. So when you call this function, the code of this function is going to take these parameters and translate them so that it can pass them to the create file function of the kernel32 library. As you can see, this function has a lot more parameters. Some of them deal with sharing of this file between multiple processes. If multiple programs try to open the file simultaneously. There's a lot of other flags that tell the operating system what to do if the file doesn't exist. So do you want to create the file or not create it? There's the security attributes parameter. That's actually a big structure that contains a lot of information about if the file is being created, what kind of permissions it needs to have. So this API is a lot richer than the C level API. Now, you can call this function directly. And in fact, many programs call this function and other functions of the Win32 API directly. So it's a little bit more cumbersome because you have to deal with all these parameters, but on the other hand, it gives you a lot more power. So once we reach this function, the code in kernel32 starts executing, and it handles some special cases, but in the general case, it takes these parameters and it does another set of translation so that it can call the ntCreateFile function from the native API. This function is exported by NTDLL. Now you can see that most of the parameters in this function mirror the parameters of CreateFile, but you have a few extra arguments. So on this level, the API is even more powerful. One downside is that this level, the native API, all of these functions are not supposed to be called by programs, and they're not officially documented. Over the years, people have reverse engineered them. Microsoft has inadvertently released some documentation. I think the anti-monopoly case that they had in the late 90s forced them to release some documentation about their internal APIs. So if you Google, you can find documentation about these functions, some of it even provided by Microsoft. But generally, you're not supposed to be using these functions because Microsoft could change their internal implementation between different Windows versions. So they don't really make any assurances about compatibility. So this function takes all of these parameters and invokes the system call interface that calls into the kernel. And all these parameters are passed into the kernel, and then the kernel implementation of the ntCreateFile API takes over and actually performs the actual work of creating the file. So this is how the system works. We traced a very simple file, a very simple function for creating a file. Many of the other APIs that your Windows programs are going to use are going to follow essentially a similar path. They will go through the API layers and finally go down into the kernel. Now, at this point, you might have a couple of questions. First one, why is this so complicated, right? The Unix system call interface is much simpler. In Unix, you basically have a system call which is almost the same as the C function. So there's almost no translation that you need to do between user space and the kernel. And also in Unix, generally the kernel interface is stable. It depends on which specific operating system you're dealing with, but on Linux, to be more specific, you can take a program that you wrote 10 years ago and run it on the latest kernel, and as long as it uses just the kernel interface, it's probably still going to work, even though a lot of the other libraries and other code might have changed, but the kernel interface is stable. So Microsoft didn't do this because they wanted a little bit more flexibility. If you limit your kernel interface so that the kernel interface doesn't change, it makes it much more difficult to perform various optimizations on how parameters are passed between user space and the kernel, and so on. So they thought it would be more convenient for user space applications to just use NTDLL and then the kernel, and this interface they considered internal. Now, that explains this. That explains the split between the kernel and NTDLL. The next question is why did they separate NTDLL from the Win32 API, which is implemented on this level? Why not just document this interface and have applications call it directly? One reason was that this interface is very detailed and provides a lot of power, but sometimes its functions are not as easy to use. But an even more important reason was that when Windows NT was originally conceived in the early 90s, it was meant to be a universal operating system that could provide multiple application programming interfaces to support applications written for different systems. And in fact, the original release of Windows NT supported applications that used the Windows APIs, applications that used the Unix APIs, and more specifically the POSIX standard. And then they also supported applications that used the OS/2 APIs. Now, OS/2 at this point is long dead, but back in the early 90s, OS/2 was a big rival. And Microsoft, well, before they became rivals, Microsoft was collaborating with IBM on implementing OS/2. But later they split. But Microsoft still intended for their kernel and their low-level system to be able to support multiple types of programs. You also have to remember that back then they didn't have the market penetration that they do now. So a lot of those they weren't so sure that their Windows API was actually going to win, and they wanted to make it easy for people to take their existing Unix applications, of which there were a whole lot, and they wanted to make it easy for them to take those applications and port them to Windows by essentially recompiling them without having to really modify the APIs too much. So that's the history that kind of explains all of these different layers. But over time, Windows kind of won the war for the desktop, and they slowly cut off support for those other APIs. And in fact, people never really seriously used them. Like the system was designed to support that, but pretty much everybody was writing Windows applications. So Microsoft slowly kind of removed support for the other types of APIs, but now we still have the legacy of this layered interface. So this is sort of how the architecture came along. So let's take a look at some of the security features of this architecture, which are sometimes surprising if you haven't looked at them before. So the first thing is that almost everything in Windows on the lowest level is a securable object. This means that all of these things that we have listed over there on the board, all of them can have security permissions attached to them. And I have highlighted in red most of the objects that you would be familiar with and the objects that most programs would deal with. Directories, files, processes, threads, devices. So all of those can have various permissions associated with them, and those permissions control which users of the system can open the files, which users can write to the files, read to the files, and so on. But in fact, there are a lot of other objects which comprise the Windows system, which are also securable. So for example, you can have a You can have a semaphore, which is used for synchronization between different processes in a multi-threaded and either different processes or different threads in a multi-threaded environment. And those semaphores can also have permissions associated with them. So you can create a semaphore, and then you can say only the following users and user groups are allowed to use the semaphore. Other people cannot. As for the specifics of the permissions, Windows has a very rich model of permissions. The standard Unix permissions just they control read, write, and execute of files. So it's not very rich. Whereas on Windows, you can create much more complicated sets of permissions. For example, you can say these users are allowed to write to this directory and all of its subdirectories, but these other users can only write to the current directory, but not the subdirectories. You can also create specific groups, and you can associate those with permissions. So you can have 100 different groups in the operating system, and you can set permissions for each one of these groups. So the full set of permissions for a file can be a very, very large list. And if you're dealing with an Active Directory environment, an enterprise environment with a domain controller, then the domain controller is going to maintain the master list of users and groups. And you can set permissions on your local file, on the local system, that use not just the groups and the users and the groups on the local system, but also apply to users in the entire domain. So it's a very rich model. Sometimes you have problems because of the richness of the model. Many times application developers or even system administrators might not realize exactly what the full permissions are. And you might end up with a file which is writable or otherwise accessible by users that are not supposed to be able to write to it. On Unix, this is less likely to happen because every time you list the files in a directory, you can see the exact permissions of all of them. So it's much easier for a human to kind of look at the file listing and say, oh, this file is writable, this file is not. Whereas in Windows, to get that kind of information, you have to right-click on each file, and then you might have to click through like 10 layers of dialog boxes to like kind of get the full picture of who is allowed what access. Also, sometimes you might have permissions on folders that propagate down to files and other folders that are contained within. So this inheritance of permissions also sometimes creates problems. So what kind of permission problems can we encounter? The obvious one is you might have an executable file which is launched with high privileges. So if you're a normal user of the system, you would not, and not an administrator, you would not normally have administrator privileges. But if there is a service on the system, a background service, implemented by a certain executable, and that executable is writable by you, you can overwrite the file, and then the next time the system boots and launches that executable, it will be launched with system permissions, but the contents of the executable would be whatever you put there, so you would be able to get your code to run with high privileges. This happens sometimes with certainly not any Microsoft software, but some third-party vendors, when they install a service on your system, they might forget to change the permissions of the file to make it safe. So that's a situation that arises somewhat common. Another problem is that not only the executable needs to be protected, but also any libraries that are loaded by this executable. This has also happened a number of times in the past with various software. Also, sometimes you would have services that use configuration settings, and those configuration settings are stored in the registry. Now, in Windows, the registry is also securable. So every key or branch of the registry can have permissions associated with it. And many times developers kind of forget that or overlook that or just set incorrect permissions. So you might end up with configuration settings which are fully writable by any user on the system. And then by changing those configuration settings, you can interfere with the operation of the service, or you might get the service to somehow execute your own code. Another interesting thing on Windows is that processes and even threads are also securable. So each process or a thread would have an associated set of permissions. And if you have a thread, for example, which doesn't have the right permissions set up, that thread might be accessible from by any other user on the system. Now, what can a user do with a thread, right? It's an interesting question, because normally you don't really think about doing stuff with threads. And in fact, most applications never have to do anything like that. But if you have a thread which is accessible by a low privileged user, the user can open this thread, and then once they get the thread object, they can look at all the threads. They can suspend the thread, then they can inspect all the threads registers, the current execution context, and then they can modify those registers, including the instruction pointer. And if you modify the instruction pointer of the thread and point it to some code that you want to execute, and then resume the thread will start executing from the new place where you put it. But the thread is still executing with high privileges because it's it's a thread in a process with higher privileges. So the code that you got the thread to execute will execute with high privileges, and it can do something bad to the system. So it is highly recommended that if you're developing Windows software, or if you're auditing Windows software, and you're dealing with those low-level APIs, it's highly recommend that you familiarize yourself with how the security system works, what are the different permissions, how to set them. And there's also a number of places in Windows where if you call the API and you omit certain parameters, and you saw how those API functions look, right? They might have a dozen arguments, and some of those arguments are, various structures. But often, if you just pass null instead of passing a structure, the API would still work, and it would just use whatever's the default. Well, sometimes that default is defaults to creating a file or some kind of other object with no security restrictions. So if you use the API and you just use the default settings, you might end up with a security flaw. So you have to be aware of the places where you have to set the security settings, the security permissions explicitly. So let's take a look at another example. This one is a little bit more interesting. I think it's a little bit unique to the Windows operating system. So in Windows, you can create named pipes. Named pipes are just a mechanism for two processes to talk to each other, right? You can send data from one process to the other over the pipe. And the pipes are named because when the first process creates the pipe, it gives it a specific name. And then the second process opens that pipe by giving it its name. So it's very much like a file, except that it's not a file, it's a pipe between the two processes. Now with pipes, you have this feature called impersonation. So this is meant for the following situation. You have a service running with higher privileges, and then you have a client that uses a named pipe to talk to the service. The client runs with lower privileges. So it's a process started by the normal user. Using impersonation, the server can say, I want the operating system to give me the exact privileges that the entity connected on the other side of the pipe has. And once it gets those privileges, the server can perform actions like opening files and doing other things on the system with the privileges of the client. And this is actually intended as a security feature because this way the server can restrict its privileges to just the files that the client has access to. So if the server needs to open a file, normally because the server runs with high privileges, the server can open any file in the system. But if it's opening a file on behalf of the client, it can impersonate the client and then try to open the file. And if the client doesn't have access to it, then the server will also fail to access the file. But there is a subtle flaw here. If clients if clients used a named pipe that hasn't been created yet, then another process on the system, a low privilege process, can create that pipe, and then all the clients are going to connect to that pipe that the low privilege process has, and they will not realize that they're now talking to the real server because they still open the same pipe with the same name, so they expect it to be the server. So once that happens, the fake server can wait for a client with higher privileges to connect to it, and when it connects to it, the fake server can impersonate the client, and because the client has higher privileges, now the fake server also has higher privileges than it had before. So whenever you're designing a system that uses named pipes, you have to be very careful to set the pipe permissions correctly and to ensure that untrusted code cannot create this pipe and impersonate you. And Microsoft has provided a number of updated APIs that make this task a little bit easier. But if you're not careful and if you don't use the more secure versions of the APIs, you might run into this problem. So here's another example of a problem that can arise with a service that is not configured correctly. Usually, to create a service, you have to add a setting in the registry. You have to add a key in the registry in current control set services path, and then you put your service name, and then you have a key called image path, which is supposed to point to the executable associated with the service. Some programs, when they install services, don't set the permissions on that registry key. So any untrusted user can modify the image path key, and then it can point that to an arbitrary executable in the system. And then when the service gets started, this executable will be executed. Here's another interesting bug that sometimes happens. It is also somewhat unique to Windows. So let's say that you installed a service, and the service set in the registry set this image path key and pointed the image path to C program files, vendor name, service.exe, but without using quotes. Is that a problem? Yes, it is. Because when the service is launched, the Windows operating system will look at this file name. But the full string can actually contain arguments, right? Because this is how you launch commands with arguments. So Windows has to somehow figure out where the executable ends and where the arguments start. And if you don't have quotes around the executable, then Windows will think, oh, you're trying to launch a program called C program, and everything else is just an argument to it. So first, it's going to look for cprogram.exe. If that file doesn't exist, it's going to look for C program files vendor.exe. If that doesn't exist, then it'll finally look for the right executable and launch it. So this is a combination of, this is a result of the interaction between two kind of features of Windows. The first one is that the API for launching executables just takes one string and doesn't really know where the end of the file is and where the arguments are. And then the second feature is that in Windows you don't have to give the full name of the file. If it's an executable, you can omit the .exe extension, and the program will still get launched. So this is so you would think this is not really a problem, because a normal unprivileged user is not going to be able to write files into C or C program files, right? Wrong. On Windows, on older versions of Windows, like Windows 2000, every user on the system had the ability to create files in the C directory, and this was by design. Microsoft just wanted to allow everyone to create subdirectories and files in the root of the drive for compatibility reasons, or because users were just used to creating their own subdirectories there. So the permissions of the root of the C volume allowed anyone to create files there. So you could create cprogram.exe and then just wait until a privileged service got installed that didn't use quotes, and then your program.exe would get launched. I think on more modern versions of Windows, you can no longer create files in the C:" directory. But you could still have a similar problem in other places, other directories. So we talked a little bit about DLL loading before. One of the problems with DLL loading is that if the program tries to load a DLL, which doesn't have the right permissions, then a user can override the DLL. But there are some other problems with library loading as well. Those problems arise from the way Windows searches for a DLL. So normally, a program loads a DLL by calling the load library API and gives it a name. So, for example, if you want to load a DLL called foo.dll, then you'll call load library and you'll give it, foo.dll. How is load library going to find that file? Here is the search order that Windows used. It's actually been changed in more recent versions of Windows, but this is the original search order. So first, it would look in the directory where the executable is. So that allowed you to bundle DLLs with your program just by putting it in the same directory where the executable is. If the DLL was not found there, it would look in the current directory. And only after this, it would look in the system directories or the path. So you would think that's not really a problem, and that's what the Windows designers thought as well, but they were wrong, because you could do something like this. You send a email to somebody, and the email would say, "Hey, check out this document," and then it would have a link to a document. So this is an Excel document, but the link uses a what's known as UNC path. This is a network path, and in Windows it's used for it's used to refer to files that are shared, that are stored on file shares on other systems, other servers. So clicking on this link would make the system try to connect to the IP address 1234. It would try to connect to it using the Windows file sharing protocol. And this also works over the internet. Unless you have a firewall in place, your machine will just connect out and try to get that document from that file share. And then the document will open. When the document opens, the current directory of Excel is going to be set to 1234/share. So the current directory of the program will actually be the file share where the document is loaded from. But remember, this file share is set up by the person who sent the email. And if that person is malicious, that file share could contain DLL files which match the names of the DLLs that Excel tries to load. And then when Excel tries to load a DLL, it would search for it in that network share first before it searches in the Windows system directories. So that was a big problem. Microsoft somewhat mitigated it by changing the order in which Windows searches for DLLs. We'll take a look at that in the next slide. But first, here's another example of where this became a problem, even if you don't have a network share. So I think this was back in maybe 2006 or so some years ago. There was a vulnerability in Safari for Windows, which not very many people use. But Apple released it, and then security researchers started looking at it, and they discovered that it was possible for a website to have Safari automatically download a file. Now, normally, if you go to a URL with a browser and that URL tries to download the file, the browser will pop up a dialog box and it will say, hey, where should I save this file? Where should I save it? What should I name it? But to make things easy for the user, in Safari, the file would just automatically get saved into the downloads folder. The downloads folder was set by default to the user's desktop. So this meant that every site that you visit with Safari on Windows could drop any file it wanted into your desktop. When this was first reported as a bug, Apple said, well, that's not a big deal. And even the security researcher who found it said, well, it's really not that big of a deal either, because the attack scenario would be you drop an executable with a funny icon on somebody's desktop, and then you hope that they click it. Now, that will probably actually work, but it's not as good as a more automatic exploit. It still relies on tricking the user to a large extent. But then people figured out how to combine this vulnerability with with the DLL loading behavior. So they used Safari to drop a DLL into the desktop, and that DLL was a DLL that Internet Explorer loaded when it was launched. Then the attacker would wait for the user to double-click on the Internet Explorer icon on the desktop. When they click on that icon, Internet Explorer will launch, and the current directory of Internet Explorer will be set to the desktop, because that's where the shortcut icon was located. So now you have Internet Explorer running with the desktop as the current directory, which means that any DLLs that IE tries to load will first be looked up in the desktop directory. But you can drop any file with any name into that directory. So now you're able to get your code loaded into a process on the user's system, even if the user doesn't click on any of the weird files on the desktop. So Microsoft tried to mitigate this, and they did to a large extent by changing the DLL search order. In XP Service Pack 2, it was changed so that first you search in the executable directory, then the system directories, then the current directory, and finally the path. So this mitigated the problem, but there's still one situation in which we can do the same type of attack if we send somebody an email with a link to a file on a network share, even with this new order. Can somebody figure out how you can get a malicious DLL to get loaded from the network share, even though the Windows system directories are searched first?
So in the first scenario, and the order is executable directory, and the second is the current directory.
Yes.
And the vulnerability is people put the DLL file on the desktop and wait for people to launch the icon on the desktop.
Yes.
And if the Internet Explorer gets all the DLL file it needs from the executable directory, right? Have to go to the current directory to load.
Because the executable directory is where the executable is located.
Yes.
And for Internet Explorer, that is the C program files Internet Explorer directory. If you look in that directory, you'll see that that directory contains just a couple of DLLs. But Internet Explorer also uses a lot of DLLs from the system directory. So, for example, Internet Explorer uses user32.dll, which is one of the standard Windows DLLs that almost every application uses. That DLL is not in the executable directory. That DLL is in C Windows System32. So Internet Explorer and virtually any other application that you launch will load a bunch of DLLs from these directories here, just in its normal execution. But because the current directory is searched first, you can put any file with the same name, with a name that matches one of the files in this directory. You can put that in the current directory, and it will get loaded first. So now the question was, on a more recent Windows system, if the search order is modified so that the Windows system directories are searched before the current directory, can we still get a program to load a DLL from the current directory? Any ideas?
Any matches, but the attributes of the file differs whenever the is successful. I think the DLL names were the same, but the second DLL also loads because some of the attributes differs.
I don't think this happens in this case. That's a different vulnerability.
Well, is there any way would it work if I put it in my own System32?
Well, if you put it in your own System32, then the person you're attacking will not be able to load it from there. No.
System32 instead.
Yes.
You know of executables that get launched from a network share that you can write to? You can drop a DLL there.
If you drop the DLL in the executable directory, you mean?
Yeah, if the executable is on a network share itself.
Yeah, but then you have to get the user to launch the executable from the network share, which is a little bit more suspicious. Now, you could send them an email that just has a link to an executable, and maybe they'll click it. But if they do that, then they'll click on anything. What we're trying to do is we send them a link to a seemingly safe document, but when it gets opened, the program that opens it, which is installed on their own system and is supposed to be safe, loads a DLL from the network share.
So is that possible we send a different icon to the user, but that shortcut point to the network share address?
Yeah, but then it'll still look. I mean, there are many ways in which you can fool the user into clicking on something that is actually an executable. But what we're trying to do for this specific example is we're trying to get the user to click on a document and then hijack the executable. Any other theories?
Could we load DLL by another DLL?
Sorry?
Could we directly load DLL by another DLL?
Yes, but as long as if all the DLLs are loaded from C Windows System, they're only going to load other DLLs that they know about. So we don't have control over what DLL is loaded. Yes?
What do you need to get it to load DLL that will be in the path?
Can you speak up?
You would try to make it a DLL that when the program wants to use from the path.
Yes. That's a good way to do it. So not all DLLs on Windows are stored in these directories. You might have a program that loads a DLL from the system path. Maybe during the installation of the program, it adds some directory to the path, and then later it loads DLLs from that directory. So if the DLL that is being loaded is normally found in the path, then you just need to put a file with the same name in the current directory, which is the network share, and then that will get loaded first. So in that case, the program will first look in all these directories, but because it's not a system DLL, it will not be found here. And then it will look in the current directory, it will find the malicious file, and it will load that instead of looking in the path. So that's a great answer. That's one way to do it. The second way to do it is, it doesn't apply to every program, but it applies to many. If the program tries to load a DLL that doesn't exist, so normally applications can still load, can try to load DLLs with the load library API, and that API call might fail, but that doesn't always break the program. So, for example, some applications might have optional plugins or other kind of optional functionality, and which might not be installed on the system. And then the application would try to load a DLL by a name, and then that DLL doesn't exist, and then the program says, well, it doesn't exist, so I'll keep going with what I have. So if you have an application that loads DLLs that don't exist, then you can look at the names that it tries to load, and you can just take one of those names that doesn't exist, and again put it on the network share, and it'll get loaded. So these are the two ways you can still bypass this protection. You can either mimic a DLL that doesn't exist, or you can mimic a DLL that exists in the path. But it is a relatively rare situation for this to happen, and some applications have actually been hardened now. Some of the more commonly targeted applications have been hardened. One way to harden the application is before calling load library to load a DLL, you just set the current directory, because you can change the current directory at any point, right? The application can change its current directory. So before calling load library to mitigate this attack, the application changes the current directory to a known good directory. And then this attack can no longer be done, because the current directory no longer points to the network share. And you can even do something like change the current directory to a safe place, do your load library call, and then change the current directory back to the network share. And this way you're not interfering with the rest of the execution, but you mitigate this bug. So we had some fun with DLL loading. Let's take a look at file access, and more specifically file paths. A lot of these vulnerabilities that we talk about are not, they don't really seem like major architectural issues. And this is because, in general, the architecture of Windows and also of many other operating systems, maybe with the exception of DOS, which was never meant to be secure because it never supported more than one user. All of these, standard operating systems are actually designed fairly well. Their security architecture is sound. The places where you're going to find the problems are the little corner cases, the places where the APIs are just not very user-friendly, so developers make mistakes. Some APIs are just easier to misuse than others. Some problems arise just because the particular implementation details of something like the DLL search order are just not very well understood by application developers and by system administrators, and even sometimes by security people. Until like Windows has existed for many, many years, but the DLL search order problem was not identified until I think sometime in the 2000s. So before then, people just never really thought about, hey, what can you do with a DLL search order? So this is another place where the implementation details are very important, and people always people run a high chance of getting their security system wrong. What we're going to talk about in this section is how file paths and file names are interpreted by Windows. Normally, it seems pretty straightforward. You give it a path which has, C:, some directories, and then a file name. But it's actually much more complicated than this. The main application case that we're going to look at for this section is the case of a web server. So you have a web server which runs on Windows, and the web server gets requests for files, and those requests in the URL would contain some path to the file and the file name, and then the web server has to take this and translate it into a path on the local file system, and then open the file, read it, and send it back to the client. So if the web server is going to perform various checks on the file name to make sure that it's valid. So usually you don't want your web server to actually serve any file on the entire system, because some of those files might contain sensitive information. So you want the web server to only serve files from one particular directory. So everything in that directory and its subdirectories can get served to the browsers, but everything above that directory or with other paths cannot. So this means that the web server has to implement some file sanitization, file path sanitization, and the web server developer has to be aware of all the little quirks of the underlying operating system, because if they miss something, then an attacker can send the request with a weird malformed name, which the web server will interpret as a safe file name, but when it passes it to the operating system will get a file that it was not meant to. So take a look at this. Take a look at the file name that we have up there on the first line. It looks totally weird. It's just a jumble of dots and slashes and stuff. But if you try to open that file with the standard Windows APIs, you will actually get C Windows Notepad.exe. This is because the dot in the beginning of the file, so this dot translates to the current directory, and in this example, the current directory is C Windows System 32. Then you have foo, which is a subdirectory, but then you have two dots, which kind of move you up one level. Then you have this slash, which is actually converted to the other slash. And then you have another two dots, which go up one other level. And then finally, you have Notepad.exe. So this gets translated into this. And if you're writing a program that needs to deal with these file paths, you need to be aware of all the details of that canonicalization, or use functions that can do that for you. So here's one quirk of Windows. If a file ends with a space or it has some trailing dots, all of those get cut off. So all three of these file names are actually the same file. They refer to the same file. So maybe your web server is configured to deny access to a file called hidden.txt. So if you're writing your web server and you want to implement a feature like this, you would, the most natural way to do this is you get the file name from the request and you just check if it matches hidden.txt. If it matches hidden.txt, then you deny the request. But the attacker can send a request that says hidden.txt and then either have a dot after it or %20. %20 is the hex code for a space in a URL, so that's basically a space. So if you send a request like this or like this, then the web server will look at this file name and it might say, oh, this file is not hidden.txt, it's some other file, so I'm going to serve it. But then when you pass this file name to the Windows API, the API will cut off the space or the dot, and then it will get the hidden file. Another thing that you have to be aware is that the Windows API accepts both the / and the \. A lot of people don't know this because if you just use the Windows command prompt, only the one / works, the other / doesn't. But on the lower level, the API actually accepts both, and it treats them the same. So if an attacker sends a request for directory / hidden.txt, if your web server doesn't know about the two slashes being equivalent, it might think that this is a request for a file where the name of the file is directory and then this character and then hidden.txt. So it might think that this is the name, and it's not actually a full path. And it will compare this with hidden.txt, and because they don't match, it'll say that's a good request, and it'll send it to the Win32 API. But then the API will say, oh, we're looking for a file called hidden.txt inside a directory called directory. So it will open the file. Another feature of the Windows file system, and this one is very insidious. I've never actually seen anybody who used it for anything legitimate. The only place where I've seen it used has been in various exploits and security problems. Windows actually supports alternate data streams in a file. So you can have a file, and normally when you open the file, you get the data stored in it. Well, on Windows, this is actually just what's stored in the default data stream. But you can create other data streams. So a file can have multiple parallel sets of data. And you can actually do this on the command line. You can say, type notepad.exe towards file.txt : foo. So this creates a file called file.txt, and it creates a stream called foo, and it makes a copy of notepad into that stream. Now, if you look at this file.txt, if you open it normally, the system will access the default data stream, and the default data stream will be empty. So it'll say, oh, this file is empty. But in fact, this file contains all of the data that you put there. So it's a way you could potentially hide data. But another thing is that the default data stream does actually have a name. Its name is data. So this is actually a real vulnerability which existed on the IIS web server. That's the Microsoft web server, version 4. So the IIS web server would normally execute ASP applications. And usually you would have the source code of the ASP program in a file called login.asp. And that file would contain the source, and that file would be in the directory that the web server serves. And the web server had logic that checked the extension of the file. So it would look at the extension and it will say, oh, if the extension is ASP, then instead of just sending that file to the browser, I will execute it as a program, and then I will send the result of that program to the browser. So this is how ASP scripts were executed, and this is still how they're executed even today. But there was a bug. If you send a request that said login.asp : %data, then the web server will look at this, and when it tried to see what the extension is, it just searched for the dot. So it would find the dot here, and it would say everything to the right of the dot must be the file extension. So the file extension was ASP stuff. And it looks like the extension does not match the normal ASP extension. So the server just takes this file, opens it, and sends its contents to the browser. But when you pass this file name to the Win32 API, the Win32 API looks at it and says, oh, you're asking for the default data stream of the file. The default data stream is just the normal contents of the file. So as a result, you get the source code of the login.asp program sent to the browser. And very often, those ASP programs would have passwords hard-coded in them, or other like internal things that are security sensitive, which the programmers thought were safe because the source code of the application was never meant to be sent to external people. There have been other similar bugs with other web servers. Also PHP. There were a number of different bugs that allowed for the disclosure of the PHP source. So this is a fairly common problem with web servers. I think at this point most web servers have been, the major web servers have been through this, and they're all fixed now. So you probably don't have this problem very often. But if you're auditing a piece of software that was written, last month by a programmer that doesn't know about the alternate data streams, you might have this bug. Okay, and then the final thing that I wanted to show you is a relic of the old DOS file system limitations. So in DOS, in DOS, the maximum file name was 8 characters and then 3 characters for the extension. And when Windows first started supporting longer file names, which was in Windows 95, they had to do something for backwards compatibility with DOS. So they implemented this scheme where every file name with every long file name would get a shorter name that maps to the same file. So this way, if you're using DOS and looking at the files, you could still see them just with kind of shortened names. And the scheme they used for this was they take the first 6 characters of the name, and then they append tilde and then a number. So for example, program files becomes progra tilde 1. And then if there was another file that also started with the same 6 character, it would become progra tilde 2. So if you have a file called hiddenfile.txt with like a long file name, even on totally modern Windows system, 10, 15 years after DOS kind of lost relevance, the Windows system would still support those short file names. So from the browser, you could send a request for hidden %1.txt. And then when this gets passed to the Windows API, the Windows API would say, oh, this is a shortened file name. I'm going to expand it into its the full name, and it's going to give you the contents of the hidden file. So this concludes the things that I had prepared for you. If you have any questions, ask me now or send me an email. Any questions? Yes.
I tried to execute the notepad that execute and that to fail.tlt, that one, it doesn't work.
Which one? Oh, I think actually you need $$foo.
Oh,
I think it was a typo in my slide. Try with a $. Yeah, I think the syntax for the data streams is actually colon percent and then the name of the data stream. Did that work?
the same result.
See? Oh. Okay. Well, I didn't actually try running it. Maybe it doesn't work from the command prompt, but it does work from the Win32 API. So if you write a C program that uses the create file API, then you can create a file with that name. Okay.
Alex,
Yes.
can you review you mentioned that some of these, you sort of gave some of them as being solved like in 2006 or 2004. Which of these issues would you say are still most prevalent today? Or what is the Windows issue that's most prevalent?
Oh, I mean, this was meant to be a whirlwind tour of various Windows corner cases, and most of these things you can still find in applications that are not the major ones. So there was a time when the IIS web server was vulnerable to a bug like this. At this point, the IIS web server and other kind of major applications like Internet Explorer and Office, they have been audited for more than a decade by many security researchers. So most of these bugs you would not find them in the major applications. But you're going to find a lot of third-party software written by people that are not security specialists, or software that is just too obscure to attract the attention of security auditors. So if the software was written by somebody who hasn't taken this class and it was never really looked at by a security person because it's not in wide use, it's not interesting enough to attract the attention of attackers, then it will most likely still be vulnerable to these problems.
Really, they're all still relevant then.
Yeah, pretty much everything we talked about is still, because all of these are just underlying features of the Windows operating system. The one that has been mitigated to some extent is the DLL search path, because Microsoft modified how the search path works by default. But we did talk about how even with the new search order, some attacks are still possible. And also I think for some of the APIs for creating device objects and assigning security permissions on them, there are now new APIs that you're encouraged to use that have more security defaults. So they're not going to create a device that everyone can access by default, like the old API would. And if you read the Microsoft documentation for the old API, it will say this API is not secure. You should use the new form, which is better. But you could still find software that uses the old APIs too. So all of these things are still in the operating system, and they're probably not going away ever. Anybody else? Yes.
Just to go back to the flaw you mentioned with Safari on Windows operating system, if I understood correctly, you said the main issue was the ability of an attacker to a user could simply download an attack-based DLL onto the downloads directory.
Yeah, but the user didn't have to click on any prompts in order for the DLL to download. You would just go to some random website. You go to like website.com.
Right, without being prompted to download.
Yeah, and then the website automatically downloads the file.
But the file is downloaded into desktop/download.
Yeah. No, it's being downloaded into desktop. I think most of the modern browsers actually also download those files automatically. But they download them into a directory called downloads, which is meant for that, not onto the desktop. I think the real flaw with Safari was that its downloads directory path was set to be the desktop.
Also, then a lot of people found DLL search order problems in installers, right? That was the next step.
Oh, yeah.
Yeah, because everybody downloads installers to your downloads folder. And there was one guy on
Oh, right, I forgot about that.
he posted
Yeah.
some comment on Reddit, and he was like, I just spent an afternoon auditing some common installers, and I found like 86 DLL search order vulnerabilities where people had not used the load library API call correctly and specified like either a full path or some kind of defined path to a DLL. And then you could, hijack that call if you had a DLL in the same directory, and sort of game over. It's not so critical, but still it was exploiting that same bug all over again.
Yeah. I mean, I guess that's still relevant.
Yeah. No, that one seems to pop up a lot.
Yes.
Another thing I was wondering if you could talk a little about is the dangers of in a multi-threaded program and changing directories at different times.
Okay, so if you have so each program has a current directory, which is for the entire program. So if you have a multi-threaded program where one thread changes the current directory, and then another thread creates a file and relies on it being in the old current directory, then I guess that's a problem. So if the attacker uses a network path, they can influence the original current directory when the program is first started. But how are they going to influence the current directory that the program changes later? So most programs don't take a directory name from like an untrusted input and then change into that. So usually if a program changes directory, it's because the user explicitly told it to change the directory, or it changes the directories to hard-coded known directories. So I guess it's not a very common problem, but something like this could happen. Okay, anybody else?
So in this case, we cannot prevent it, right? Only Microsoft can fix this.
Well, this is not really a bug in Windows. It's a bug. So if you have this bug, the bug is in the application that tries to sanitize the file path, but it doesn't take into account all the corner cases of Windows. If you actually read the Windows documentation on what do file names look like, the documentation will tell you about all this stuff. But the documentation is not really read by most people, so that's why they don't know. I mean, Microsoft could kind of mitigate this problem by removing support for these alternate data streams. But a lot of these features are maybe used by like a small percentage of programs. So if they just start removing them from the APIs, then they'll break compatibility with alt programs. So in a lot of these cases, the security community has just accumulated over the years a large set of kind of known bad patterns. So here's what to look for when you're auditing software. And all of these patterns are part of that kind of knowledge set. And then if you're training developers on how to avoid these problems, you give them the list of things not to do. If you're training people to do security audits, you give them a list of things to look for. And there's really no other way to fix that for Microsoft without breaking compatibility. Usually, a lot of these problems are mitigated by other higher level languages. So, for example, if you use .NET or Java or Python, some of these problems might not arise because those systems might not allow you to use like the lower level APIs where those vulnerabilities happen.
They would have other problems exactly like these that you would need to know about.
Yeah. So it's possible to, like, if you prevent the programmer from reaching one of these weird corner cases, then you would mitigate the vulnerability. But you might introduce new vulnerabilities if your new potential vulnerabilities if your implementation of something doesn't match the underlying operating systems.
Yeah, I guess the point I'm trying to make is that you need to understand the tools that you're working with to build the applications that you want to secure, because everything's going to have corner cases. You can't just go into it blindly and think that you've done a good job at opening files and creating permissions on top of them and securing the objects and whatnot, unless you've actually done some investigation to figure out what you're working with. So, you guys need to be able to do this and investigate these kinds of corner cases in whatever system you use. And it's going to be especially important with your assignment. If you guys are trying to write a sandbox, you'll need to be familiar with all of these for whatever system that you end up using. So it's definitely your responsibility to not only know what the issues are, but also how to fix them.
Yeah, I almost wish we'd had you out a week later so that everybody would be asking,
Yeah. But that's good. I mean, not everybody's going to write their sandbox in C.
I'm sure they'll forget some of it.
Yeah. And there's plenty more that Alex didn't go over. I mean, this is just the kind of easier to describe things that are like right in your face. But there's tons of little issues exactly like this. We could go on forever. And they're all documented in your textbook. So, by the way, if you want some tips about how to avoid the rest of them, they're in the textbook.
Certainly not all.
Most, yeah.
A large number of them.
Yeah. And for Windows only, right? They're not going to just, like, the Art of Software Security Assessment isn't going to describe what these kinds of corner cases look like for Python or for stuff that's not the Windows API or stuff that's not straight up POSIX. Or actually, I think they actually go into.
They talk a little bit about Unix, but not. I mean, there's plenty of other stuff.
Yeah.